Welcome back to Code Meets World, and in today's episode of me solving the NeetCode 150, I'm going to be moving on to problem number 10. Last time, I'm in the linked list category right now, which is giving me lots of problems, I must admit. Last time I solved the merge two sorted lists problem, and there's a third easy problem in this category, which is called linked list cycle. So I'm going to move on to that one, and I will be very glad to move out of the linked list category. I definitely need to work on these. I'm gathering. Okay, so the problem title sounds pretty self-explanatory, but let's see. Let's read the instructions. So given a head of a linked list, determine if the list has a cycle. And a cycle is defined as the linked list having some node in the list that can be reached again by continuously following the next pointer. Internally, there's something called POS, I guess for position, is used to denote the index of the node that tail's next pointer is connected to. POS is not passed as a parameter. So we just return true if there's a cycle, false if there isn't. So let's see what this is talking about. So if we're given that head is 3, 2, 0, -4, position is 1. Oh, I see. So position is saying the end of the linked list points to position index 1, and this is index 0, so it points to here. That's a cycle. This is 1, 2, and the tail of the list points to index 0, which is 1. And again, I don't get this in the function. This is just so internally they know how to set up the problem. And then this last one, the position is -1, which means the end of the list isn't actually pointing anywhere. So we can have a lot of nodes. We can have all sorts of values. Right. Okay. Let's head down to the whiteboard and think about this. Let's look at this one. Because I currently don't have any ideas on exactly what to do, though. I'm going to think through this. And so all I'm given is a head pointer to this first node. One thing that's coming to me is a trick I'm remembering from the days where I was studying this, which is to use the concept, I'm going to call it staggering. Oh, I think my professor actually called this the walker and runner technique. Don't quote me on that. But what I'm thinking is this. We'll have some pointer x that points here. And then we'll send another pointer, say y. And we'll send y all the way around the list. So first it would point there, then it would come here, and then we would keep following it. Y would eventually come around to here, and oh, y and x equal the same thing, so we must have a loop, and that works in this small case. But in this bigger case here, in example 1, for instance, if we started with a 3, gotta change colors. If we started with the 3 and tried this technique of sending some other node around, it would come here, then here, then here, then it would come around back to here. And we've never hit this one, so we're not sure that there is, like, what I'm saying is the loop is up here, but we don't know that. We don't know where the loop is. So I don't think the technique of just having one stationary node and one moving node is going to work. That's why I think we need this staggering or walker-runner approach, where we actually have both of these nodes moving at the same time. So let me think about that a bit more. So in the case where we have that simple example again, I'll call my walker W and my runner R, and these are just pointers. And they can both start in the same place. But what I'm thinking is the walker moves once per iteration, but the runner moves twice per iteration. So the walker's going slowly, the runner's going more quickly. If they ever meet each other, I argue, we have a loop. So basically, they start out like this. The walker moves ahead 1. So the walker is, let me change colors again. The walker would now be here. The runner moves ahead 2, so it would go 1, 2. So the runner would end up where it started. On the next turn, the walker would move ahead 1, so it would move here. They're now equal, so we could check and see that. The runner would move 2, so it would go 1, 2. So the runner would stay in the same spot in this particular case. Now they meet each other. Because they met each other, there must have been a loop somewhere, and so we can return true. Let's see if this works for the other case, and if it does, I think this is a good solution. So the other one was, I think it was like 3, 2. The actual numbers don't matter at all. And I think it went like this, right? Yeah. So let's see if the walker and runner work here. So we set walker and runner to be the same thing. Then we move walker ahead 1. We move runner ahead 2. They're not equal, so we keep going. Walker moves ahead 1. Runner moves ahead 1, 2. They're not equal, so we keep going. Walker moves ahead 1. Runner moves ahead 1, 2. They're equal, so there is a loop. I think this will work. So let's go to the code and try it out. I'll be quite thrilled if this does work, because this walker runner thing is something from several years ago in uni. Okay, so all I have access to is head, so we can say walker equals head and a runner equals head. Oh, I guess what I don't know here, how do I know when I've gone long enough that there isn't a loop? I guess if I hit none, maybe? I'll think about that in a second. So while walker so basically while walker, if either of them find a none, if the runner finds none, I know that there aren't any loops. But if they find each other, I know that there are. So while walker does not equal I'm just going to say while true again, just for now. I never know what to put as the condition in these loops. So basically if walker is true, sorry, if Walker is none or runner is none, there's no loop. Otherwise, Walker equals Walker dot next. I think actually I want to pull this out and say it like this. If either of them are none, we return. Well, I guess they're both the same. So this, all of this can just be if head is none, we just return false. So we set both of those up. Or if head dot next is none, we can return false. So then we set Walker and runner. And then we can say while true, Walker equals, or actually I just want to kind of start them out. So Walker is head dot next. This is head dot next dot next. So if runner equals none, we can return false. It's basically the same thing. Or if either of those, sorry, not false none. If either of those are none, we can return false just straight away. Else we can say, we don't really need this. We can say if Walker equals runner, we can return true. If neither of those happen, we can say Walker equals Walker dot next, runner equals runner dot next dot next. Let's see how that works. That's what I think we need to do. Oh, right on. Let's see if that is a winner. Incredible. Very happy to see that. I am very pleased with that solution. It probably could have been even simpler. I maybe could have combined this with these. But that worked. Again, it beats 98% of the other solutions. Super, super pleased with that solution, especially given how poorly I did on the first two linked lists. So let's go ahead and mark this one as complete. And I've now done all the easy linked list problems. I've done 10 problems overall. So I'm a 15th of the way there. And I'm having a ton of fun. I hope you're enjoying watching. And thank you so much. I'll see you in the next video soon.